Okay, so this is our official beginning. So once again, welcome all of you. Okay, so as I just said, we will take this course from wherever you left off. Okay, so part of the reason to have 3 lectures a week is because we can do things in a leisurely fashion. That means I want the course to work for you. So if the pace is not good, especially if it is too fast, but even if it is too slow, then you should provide feedback. Especially if it's fast, I would like you to provide resistance, saying that, hey, this is not okay. Just slow down a bit. Let's do examples. Let's do discussions, whatever. In class, I can look at your faces and sort of try to make out how it's going. Here, it's more difficult. Okay. So one thing to decide in this course is at what degree of generality to operate. So last semester, you basically discussed only real numbers, and you were always every set was really just a subset of real numbers. Real numbers are a subset, and functions were from R or a subset of R to real numbers. So for several reasons, we want to be more ambitious this time, and we want to generalize. There are several reasons for this. One is we want to do calculus in many variables. So I should start writing down. So you studied functions from R to R, or maybe subset of R. So let's change that. So where so for example, if S is the set of natural numbers, then such a function is otherwise known as what?
Sequence.
A sequence, right? And then you studied what it means for a sequence to be convergent. Then you studied for what it means for a function to have a limit points, for a function to be continuous. So we will revisit these notions today, and then several other things. This semester we want to do as a subset of R and related analysis, which is limits, continuity, derivative, max, min, and Riemann integral. Right? Okay, so this time we want to study functions from S to Rn, with S also a subset of some RL, let's say, right? So we are going to be doing calculus of several variables, and we will do everything in the list above except for integration, which we will do in a later course. So a question to mostly, and at times also work with complex valued functions, so Cn. So one question to ask is, what level of generality are we going to work with? So last semester, real numbers was great. And then you started out by saying that, well, real numbers, you didn't really quite construct them. But what did you start out by saying? Real numbers was anything that satisfied certain properties. What was it?
There needed to be a field. There needed to
Correct.
be an order on the fields. There needed to be an ordered field, and it also had to be complete.
Correct. So field means you needed to have 4 arithmetic operations. Then order, you needed to have this trichotomy, right? Any two numbers had to be comparable, and some properties, right? That, for example, if you added, you could add the same number to both sides of an inequality. Right? You could multiply an inequality by a positive number, etc. Some axioms were there. And then this crucial thing was there, completeness. Right? Okay. So this time we are going to be dealing with functions from from some, if you will, vector spaces or subsets of a real vector space or complex vector space to another such vector space, maybe itself. This is clearly a generalization, right? If n or f, if n and l are 1, then you're back to the earlier situation. So we could say we could do everything concretely with Rn, but there are several reasons why you want to be more ambitious. So one thing is that you want to have an eye towards complex analysis. So you want to be able to say what a complex derivative is, for instance. So we would like to have some ambiguity in the field, that instead of r to the n, maybe we want to call it some k to the n, where k is the field k is either real numbers or complex numbers. Okay. But even more than that, we also want to think of spaces of functions. Okay, so this is an important thing, which is, when we thought of collections of things, those things were generally numbers, and there were functions from sets of numbers to sets of numbers. But one also wants to do analysis where the space that you are thinking of itself is a set of functions. So somehow you want to think of a function as a point in some space. And then you want to say, well, what does it mean to say one function is close to another function? What is the size of a function? So such things are done in functional analysis. And this is a very important thing. Even if you're interested just in real analysis, just one variable situation, such things do come in. They're important. So we want to have a setting where we can talk about these many different situations under one umbrella. And there are various ways in which you can do this. So I'll just list 3 sort of axiomatic settings that one can operate in. They're progressively more general. So but also some other okay, so this is not really a sentence, right? Okay, so this is a bad sentence. Let me. So want to do analysis in this situation but also more generally. Sometimes at least, okay? So some settings for this. So a non-linear space. This is a definition that we will make today. And we will see why such a definition is desirable. Non-linear space. Or we can also do more generally with metric spaces or a topological space. Was a metric space defined? No, okay. All right. So the way this works is that every non-linear space will be a metric space. Every metric space will be a topological space. And we will define all of these, but we will primarily work in the first setting of a non-linear space. And even then, we will mostly think of the situation where this space is just Rn. However, I'm happy for you to operate in any one of these three settings that you are comfortable with. So you can use whatever language you are comfortable with. We will set up the language for all three. You will take up metric spaces more generally in a later course, and topological spaces you will see when you do your topology course. So this course is really nice because we will see many examples that can be generalized in, we will see situations that can be generalized in many ways. And it's sort of something that opens the door to many different kinds of mathematics. Okay. Any questions so far? Yeah. So again, this is going to be our main setting. And as I said, I will define everything. We will take it up from wherever you left off last time. Okay. And we will also do a review as necessary. But a couple of things. One is that a lot of the things that you did last time can really be black boxed. For example, we certainly won't need proofs that f of x equals a to the x, where a is a positive number, is actually a well-defined function where x can take any real value. Right? So you did that last time. Or for that matter, that sine and cosine, what are their rigorous definitions? So such things we will not need to sort of unpack. But this being analysis, estimations will be required all the time. So, analysis is really the art of estimating things, and that will be required all the time. So there will be epsilon delta arguments all the way through. And okay, so what is kind of a very basic thing that you use all the time when you do epsilon delta arguments? So for example, if you remember last time, then many times when you needed to bound something, right? So given any epsilon, you needed to have some delta such that something or the other needed to be less than epsilon. Then at times you took epsilon by 2. Then at times you took epsilon by 3. What was the idea? I'm just asking for heuristics here. If your target is to bound something by epsilon, then at times you took epsilon by 3, epsilon by 4, whatever. So what was the idea of doing such a thing?
Usually if it's epsilon by 3, then you separate the actual function, the upper bound of region around the upper bound and the region around the lower bound. So you add them up to get epsilon, and that's why.
Okay. So what is the thing? So typically if you have epsilon by 3, then maybe you are taking 3 of them together and adding, and somehow combining that to a single bound with epsilon, right? So what is it that allows you to do that? The basic tool?
Triangle inequality.
Yeah, right. So sorry. So several people saying, but somebody did say triangle inequality. And that's a very basic tool, right? So the idea is that sum of two absolute values is absolute value of a plus b is cannot be, has to be less than or equal to the absolute value of a plus absolute value of b. So this is going to be a crucial thing. You use this all the time. And in a normed linear space, this is something that we are going to abstract, the triangle inequality. And for that matter, also in a metric space. Okay, so let's get started. And to begin with, I just want to write down the definition of what it means to have the limit of a sequence. So I'm just going to write this down from last time. So so Sn be a sequence in R. So I just have a sequence of real numbers, formally a function from natural numbers to real numbers. What does it mean to say that this sequence converges to some real number S? So I'm going to put this quotation marks, limit as n approaches infinity of Sn equal to S. So we say where S is also a real number. Okay, so if the following happens. And so this is, of course, a definition. So what's the definition? All right, so I'm going to write something. There exists a delta greater than 0 such that for all epsilon greater than 0. All right, shall I continue?
No, for all epsilon.
Yeah, so of course this is, well, I intentionally wanted to make a mistake, but I was looking at the wrong parts of my notes. So anyway, so this is a failure. The point is, okay. So of course I was writing something about the limit of a function, but the quantifiers were in the wrong order, right? And I was hoping that you'll catch it, but it was the wrong. Anyway, so let's write down the correct definition and maybe somebody can tell me what happens. So a picture, right? This is S. And what happens is that eventually all the Sns will fall in any given window, and you can make this window as small as you like. Correct? So if I take a window of this size, then beyond a certain point, all the terms in this sequence will fall within this window. If I make the window smaller, then maybe I have to go further down the sequence, but even still the same thing will be true. Right? And no matter what size window I take, the same thing is going to be true. Okay. So how do I make this a definition? So definitions of this type, after having spent a semester, should really just come out without effort. Right? So how do I start?
Where exists n such that.
Okay. All right. Okay. So let me write that down. Good.
So for all epsilon there exists n.
Okay, so this is a question, right? For all n there exists an epsilon. For all n there exists an epsilon, or for all epsilon there exists an epsilon.
For all epsilon there exists.
Okay, so you see, this is like a challenge and an answer, right? So before there is an answer, there has to be a challenge. My challenge is that I want to show that my challenge is a small window epsilon. And it is only after I give you a challenge that you are going to say that, oh, okay, you need to go this far down the sequence so that everything after that is caught in that window. Right? So this point should be absolutely clear to everybody. Let's write down the definition. For all real numbers epsilon greater than 0, let's write separately this. There exists a natural number capital N such that what happens?
N greater than equal to capital N implies Sn minus S is less, mod Sn minus S is less than epsilon.
Okay, all right. So let me write this in a certain way such that for any n greater than small n greater than capital N, what I want to say is that eventually all of the numbers, so let's say this is Sn, right? So this is the window of size epsilon. So that means what is this number? This is S minus epsilon. This is S plus epsilon. And you are going to say that all the Sns lie within this window, right? So this is a general N. So I'm going to write it in this fashion first. S minus epsilon and S plus epsilon, this window catches all the numbers, all the elements of the sequence beyond a certain point, correct? So let's say this is Sn. Okay. So that picture also I want to be part of it. Okay. Okay, so this is a definition. Now imagine that I want to generalize this. So what did we say? We wanted to have functions from subsets of Rn to Rn. So first, let's just think of sequences in Rn. Right? So want to generalize this. To so what this means is that i.e. Sn is a vector in Rn if you want for all n. Does it work?
Sir, that inequality will need to be examined. S minus epsilon less than Sn less than S plus
Yeah, so you see, so this is a problem over there, right? So first of all, I want to, okay, so I want to have this notion of smallness, and I have notion of smallness for real numbers. So maybe I want to keep that epsilon the way it is. That's why I said real number. So epsilon is still a real number. Okay.
Excuse me, sir.
Yes.
Sir, the Sn and the Rn, the both ends are different, right?
Sorry. Yes. Thank you. Thank you very much. Yes. So let's use L maybe. Maybe, well, I don't know. So, or M. Okay. Yeah, so you see that real number epsilon, maybe I want to keep the same. And this is a sequence. So the capital N being a natural number also is going to stay the same. But the inequality that I wrote over there is really nonsense now, because there are several problems. One is that S minus epsilon doesn't make any sense anymore, because S is a point in Rm, correct? See, if I have a bunch of points in Rm, then it's going to converge to a point in Rm. It's going to converge to something of the same kind. So that S minus epsilon makes no sense.
S minus Sn non less than
Right, exactly. Okay, so we'll come to that. But also the inequality makes no sense, because what does it mean for one vector to be smaller than another vector? Right. And so that's why, I sort of purposely wrote like this, but this is really equivalent to saying, so i.e. we can write this in the form that somebody answered right in the beginning. Instead of looking at this interval and saying that Sn lies in this interval written in that fashion, what we can say is that the distance between S and Sn is small, right? So at least I have made some progress, is that I can say S minus Sn is less than epsilon. And I put that absolute value because I do not want to have this inequality on both sides. Saying S minus Sn is between minus epsilon and epsilon. I could have written it that way also, right? But I'm thinking of this really as a magnitude. So S minus Sn is less than epsilon. And so for real numbers, the two definitions, the two inequalities that I wrote, they really are synonymous. But the second one is at least begins to be better in the sense that S minus Sn, when both of those are vectors in Rm, I can certainly make sense of at least S minus Sn, right? Because it's a vector. And if you think about it, these vectors, just think of it visually in the plane. There is a bunch of points, and if they're all sort of falling into a point, say a sequence. So we do want to say that if I take the difference between those 2 points, then that's going to be a small thing. So the question is, what does it mean for something to be small? So we have gone away from inequality. See, for real numbers, I have various structures. I have the arithmetic operations. I also have order, and I have the notion, and it is complete. For vectors, I do not have the order, but I do have the notion of when two things are close to each other or not. And I can do that by taking their difference and seeing if that vector is small. So So what I'm trying to say, maybe in a long-winded fashion, is that it is useful to have a notion of whether vectors are big or small. And do we have such a notion?
The magnitude of the vectors.
Right. So magnitude of the vector, we have a well-defined notion of what the magnitude of a vector is. So let's revisit this. And so I want to change this definition. So let us say that this is a so now I'm going to have the same depth, exact same, correct? So this is now a sequence in Rm. So let's see what other changes are required. So each one is a vector. So of course, if this sequence is going to converge, it is also going to converge to a vector in Rm if the following is true. Okay. Does the first thing change for all real numbers epsilon greater than 0? And the answer is no. Okay. So maybe this interval is not really very useful. But what changes? And then this one is not really useful to me. So I'm going to cross this out. But what changes? I have to have the notion of the magnitude of a vector. So I'm going to say instead of absolute value, I'm going to put this notation. So let's write this down. The same definition works if we interpret length of the vector.
Which length? There are many number of ways to define it.
Right. Okay. So, but yeah, correct. So we will come to that. So so that's the big begs the next question, right? What do I mean by the length of a vector? And I'm really thinking of this in terms of, your school. There was only one length, the Euclidean length, but we will see that there are several. So length of the vector, let's call this V, length of the vector V. So let's write this down. In school, from school.
Also, is there like proof that the vector spaces cannot be totally ordered? Are m greater than equal to 2 onwards?
Correct. Okay. So, so you have to sort of clarify this question. What do you mean by they cannot be? I mean, of course, as a set, a vector space is, R to the n has the same cardinality as R. So, so I'm just making a ridiculous point over here. Is that if you just want to put some order on the set, there is.
Yeah, but that will be partial order, like just with the magnitude, I think.
No, what I'm saying is just put the set in bijection with R and order. That's a ridiculous answer, correct? Okay. So your question really should be, can I order a vector space such that
the vector space structure preserved?
What does that mean?
Like a plus a is less than equal to b, then a plus c is less than equal to b plus c, something like that.
Okay.
So a plus c is less than equal to b plus, if a is less than equal to b.
Right. So good question. So certainly ordered fields are, so you're saying vector spaces rather than
other than fields, we only have the multiplication defined. For vector spaces we have the addition. So addition.
Right. Yeah, so
I saw the proof that complex number cannot form an ordered field.
Yes. So for ordered fields, yes, correct. For vector spaces, I don't know, but I'm sure that this question has been looked at. So maybe we'll look at that. You can also look up, and then maybe in next class we will see the answer.
Okay.
Okay. So, but from school we have one length, right? So let's write this down. So for V equals, let's just write it down as a row vector, Vn or Vm, sorry. We had, what was V? Well,
root of squares of Vi.
Exactly. So let's do this. So it was V1 square plus up to Vm square, and then I took square root of that. Okay. All right. But again, for for good reasons, it is useful to have multiple notions of length. So what we will do is that we will axiomatize what do I mean by a good notion of length into what is called a normed vector space, okay, normed linear space. But it will be useful to have okay, it's not several, a more general notion of length. Where this will just be one example. The above will be, and this is nice. So just bear with me for a definition first, and then we will see many nice examples. And I can give you some problems then. Okay, so definition. And later on, we will say that even over complex numbers, it is okay. But for now, just think of this as Rn. Okay. A norm on V is a length function. So this has to be a function from the vector space to the set of real numbers, but it's a length. So we want our length to be never negative, right? So this is going to be a function, is a function from, and this function is going to be called this. Rather than sort of the prefix notation, we have an infix notation for this function, if you will. I don't know if that makes sense. So from V to the set of real numbers, but greater than or equal to 0. Satisfying some properties. And they're very reasonable properties. So one is that you want everything to have positive length except for the 0 vector. Right? So and of course, the 0 vector should have 0 length. So for all x and v. The next one is a scaling operation. So remember, this is a real vector space. So I want it to be compatible with the real scaling. Right? So if I multiply a vector by 2, its length should also become 2 times the original length. So, so generally speaking, I said that we will look at Pramad's notes as a guide. So notation also, to the extent possible, I will follow, so that you have his notes which are typed, and also of course we will have our class notes too. So lambda times x, where lambda is a real number. So you tell me, is this correct?
I think we need magnitude of
lambda. Right. So lambda could be a negative number. So of course, if I scale a vector by -2, I want its length to be multiplied by 2. So I have to put an absolute value here. And of course, this absolute value is the usual real absolute value. Okay. And third, the all important triangle inequality, which is to say that if I take the length of x plus y, then that can never be greater than the length of x plus length of y, for all x and y in V. So this is the triangle inequality or subadditivity. Okay, so several things to say, right? I mean, first we should look for examples, right? But one thing I want to say is that just imagine if this was a vector space over complex numbers instead of real numbers. So in other words, over here, if I put complex numbers, so does the definition make sense?
Yes, sir.
Yeah. So only in one place only in one place real numbers are really coming into picture, right? That is number 2, the scaling axiom. So now what I would like to do is that not just for real numbers, but if I'm doing scaling by a complex number also, I would like to have the same property. And in this case, of course, I have to interpret the magnitude of a complex number in the usual sense of the magnitude of complex number. Okay. So notice one thing, the length is always real. I'm not making the length to be a complex number. I want to do estimation with this analysis. So there needs to be a magnitude. Length is always a real number, but I allow myself to scale by a complex number. And so the absolute value of lambda in that case will be the usual complex magnitude. So let's do it this way. So definition, let's do it over here and let's say 1. Oh, sorry, that's I need a different one here. So okay, maybe I'll just put a bullet point and with V vector space over complex numbers. Again, just to emphasize, norm is a function from V to where 2 becomes the exact same thing for all lambda in complex numbers and x in V, where for lambda equals a plus bi, absolute value of lambda is, well,
Root of a squared plus
yeah,
b
so it's the
squared.
usual one, right? Okay. Here I don't mess with this, okay? I do not think of C as R2 and put some other kind of length over here. Remember, complex numbers is a field. It really has to work well with just the multiplicative structure also, right? This norm does not just satisfy triangle inequality, it's also multiplicative, okay? So mostly we'll be talking about real vector spaces, but we will deal with complex derivative also later on. So we do want to have that. Another thing to keep in mind. Okay, so we'll come to that later. But first, examples. Are we on time? Okay. V is equal to Rm, a class of examples. And so let us take P is equal to, P is really any positive number, let us say. Okay. And then I define the following. Okay. I define so define for, so let's take some x in here. For x equal to x1 up to xm in Rm. So this is going to be something related to the number p. And so the idea is that if you look at this formula, so here I had v's instead of x's, but I took the second powers, I added them, and then I took the square root. Okay. So I just replace this number 2 by a number p everywhere. Okay. So I take pth powers, I add them, and then I take the pth root. Of course, I'm taking roots here, and I want positive numbers. So I do have to take absolute values. So here is the thing. So I take absolute value of x1 to the p plus absolute value of xm to the p, and I raise it to the power 1 by p. Okay. So so this is one definition, and I'm also going to make, okay, so okay, let's stick with this for now. So our earlier case was that earlier situation, or a school situation, was p is equal to 2. Oops. Okay, so let's take a look at this. Is this a norm? Okay, so first of all, let's look at properties number 1 and 2. Okay, so the first one was that, okay, so even before we start, this is always supposed to be a non-negative number, right? And it is, because I have taken absolute values of all those coordinates. Yeah, whether real or complex doesn't really matter. So this is going to produce a positive number, and it's a non-negative number, and it's clear that it's going to produce 0 exactly when the entire vector is 0, right? So the first property is okay. How about the second property? If I multiply all the x's by the same scalar lambda, whether real or even complex, just check. This is okay, right? No issues, because when I take the pth power, this lambda to the p will come out of every factor inside. Then I can take it out, and then the outside 1 over p power will take care of that. So I will really get the, so it really is the triangle inequality which is the issue, right? So here's an exercise. So 1. One, and we will do this in class. I mean, number 3. So 1 and 2 are clear. Three, triangle inequality is true if P is, anyone happens to know this?
Greater than equal to 1, I think.
Yeah. So the exercise part of it is prove. Yeah. So prove this.
From concavity or from the Jensen.
So right. So okay. So right. So there is, I think, something called Holder's inequality, right? So we will do this in class, but you can take this as an exercise. So several things. So prove. So we will prove this in class. Let me just say orally that try to prove this. What goes wrong for p less than 1? And certainly for p equal to 2, we should be able to do this, right? Because it's our ordinary length. And for ordinary length, we believe visually that triangle inequality holds, correct? So this is what Cauchy-Schwarz, was that discussed sometime, or maybe you saw it in school? In any case, we will do all of this, but do try to do this on your own, okay? So interesting cases. So let me just say, prove this. What goes wrong for p less than 1? But here, just I'll do something and then you. So special case, p equal to 1. What is that?
This is the standard absolute value.
Right. So this is the standard triangle inequality, correct? What you're going to be doing. So p is 1. So there is, so you're just, so p equal to 1. So here we have, this is just x1 plus x2 plus up to x. And is clearly a norm. The usual triangle inequality, which you can do by hand again if you would like, but you know, this is something that, okay, so this, all right, so this is one thing. But then, okay, so I think I should, so examples, so this is really a class of examples, right? But now I'm going to define yet another one. So Rm with the infinity norm. So we define here, what is this? Okay, if you have not seen this, this is interesting. This is just a maximum of okay. All right, so now I want everyone to just take a minute and see that this is actually a norm. So certainly I'm taking maximum of a bunch of absolute values of numbers. So it is going to be non-negative. It's the maximum. So the only way this can be 0 is if all of them are 0, which will happen only if the vector is 0. So this is all right. How about the scaling part? It's okay, right? If I scale each coordinate by something, its length is going to get scaled by, I mean, its absolute value is going to get scaled by the absolute value of whatever you scaled by. Right? It's an unnecessarily long sentence saying something very simple. The triangle inequality is slightly interesting, correct? So this is something that you should write down for yourself. Okay. It's a simple proof, but you have to take the maximum in the appropriate order. Okay. So this is a very easy proof, but I'm going to say check 3. Small exercise.
This p norm as p goes to infinite, this essentially goes to that infinite term.
Yeah, exactly. So this is, so it's a very natural question. Why did I use the same notation? Earlier I used the subscript p over there, and here I use the subscript infinity. So again, exercise. So this is exercise. So check 3, and in what way is, sorry. Oh, I'm put that in quotation marks because it makes no sense. No, p is not a real number. But somehow it suggests that if I take that p and somehow take the limit as p approaches infinity, then I'm getting this. Check this. Right.
If this happens, then from the triangle inequality of the first one, we can also take limit both sides.
Okay, but you well.
Yeah, this might be easy from other steps also.
Right, but you see, just by doing it by hand is much easier. Because you see, taking limit with inequalities, you have to again be a bit careful, right? So Okay. So please do these exercises. And out of these, we will certainly do the triangle inequality for a general P greater than 1. We will do in class. So, all right. So, any questions so far? Okay. So, what is worthwhile to do is to draw some pictures with these definitions. And so let's draw some pictures. So again, a definition. This probably was done last time, but so let us make some sort of ad hoc notation, or maybe not. Let's just say it in words. Okay, so an open ball of radius r with center x in my non-linear space. Did I make a so okay, remember my non-linear space was V. So center x in a normed linear space V is the set, exactly what it is, y in V such that okay, so I should have said something else, such that the distance between x and y is less than r. But what is the distance between two things? I should really have made that definition. I'm sorry. So definitions. So in a non-linear space V, the distance between x and y is the norm of x minus y. For x, y in okay. And an open ball of radius r with center x is simply the set such that the distance between such that x minus y is less than r. So r is some real number here. And closed ball, while we are at it, let's define closed ball is y in V such that the distance between them is less than or equal to r. Okay. So let's draw some pictures. And I think if I recall the notation, this is some notation like B sub r of x. Is that right?
So, and it's the closure of the bar. I think closure.
No. So this is the open ball, right?
Yeah.
Right. Okay. So I mean, okay. Different authors may have different. So I'm writing the radius as a subscript and the center as inside the parentheses. And this one is drx bar. Now the bar notation has a different meaning, right? So last time, did you in your last course, did you use this bar notation for some sets, for sets of subsets of real numbers?
I don't believe so, sir.
Okay, all right. So for now, just this entire thing, just think of this as a notation. The notation bar has a meaning for an arbitrary subset, which we will come to later on. And at that time, we will see that that definition is consistent with this notation. Okay, but for now.
Hello, sir. Sir, the specific properties that we have assumed, I mean, as per we have defined for norm, with
Right.
that, can we derive that the distance between x and y is same as that between y and x?
Let's check, no? Okay, so the question is, can we see that the distance between x and y is the same thing as the distance between y and x? So what does this amount to showing? This amounts to showing that the norm of a vector v and the vector minus v are the same. Is that clear from the definition?
Yes, sir.
So from what is it clear?
Sir, I mean, with if we can show that the norm of v is same as norm of minus v, then we are done.
Correct.
In that context.
Correct, right. But why is it true that the norm of v is the same as norm of minus v?
With the triangle inequality, we can say that norm of v minus v is less than equal to norm of v plus norm of minus v.
Okay.
And that
or
is.
Does that really help you? No. Okay. So norm of, but that just tells you that norm of v minus v, but that's 0. So 0 is going to be definitely less than the sum of two norms. Right?
Yes.
If we take lambda is equal to -1.
Right. Exactly. Right. So you see, if I in number 2, if I take lambda equal to -1, that just does the job. Okay. But the general point, sort of what in the direction in which he is thinking, that is interesting, which is to sort of say that what properties can I derive about the distance function from the norm function? Okay, so I was not planning on this, but we may have just about enough time to define what a metric space is today. Right?
Sir,
yes.
Sir, we use the bar notation for extended real numbers.
Okay, so then this is okay. This is a different notation.
Okay.
This is different. So, but you define limit points of a set, right?
So if we have a convergent sequence in one, which converges with respect to one norm, then will it converge with respect to all of them?
Right. So all of those things we will do in loving detail. Okay. So. But sorry, this is getting slightly out of hand because I'm veering from my plan here. Okay, so what? Sorry. So everything we will discuss, right? But right now, what I just wanted to say was, so how much time do we have? We have about 15 minutes. Okay, so this is what we are going to do. We will draw some pictures of. We'll draw some pictures of these balls for the various kinds of norms that we have considered, right? At least 3 basic ones we have a good idea about, namely the norm where I have this infinity norm where I'm just taking the maximum of the sizes of coordinates. Then when it's 1, I'm just taking the sum of absolute values and the usual length. Okay. So we will draw some pictures. Let's do that first. Okay. So, and let's do this in R2. So balls in R2. With respect to 1, 2, and infinity. Okay. By the way, even before that, what happens if I'm in R1? What are these norms in R1? Just check the formula.
They are the open and closed intervals.
That is true. Those are the balls. But I'm just asking you, just as a sort of, just a temperature check. If m is equal to 1, then what are all these different norms? P norms for various values of p.
Mod x.
They're all the same, you see. Because there is no sum inside. It is just x1 absolute value to the p to the 1 over p. So I'm just getting absolute value. So all of those norms are really the same norms when I'm taking the usual real numbers, right? And even the infinity norm, I'm just taking the maximum, but there is only one slot, so there is no maximum to take off. So they're all the same for m equal to 1. Let us see what happens when m is equal to 2. Okay. Okay, so balls in R2. So let's draw the ball. So balls, let's say just around the origin, right? So B, B R, I'm forgetting my own notation, around 0. What happens? Just take a minute to think about this. Which one is the easiest to do?
The 2 norm, that is just a circle.
That is just a circle. That, I mean, okay. So if you think from first principles, actually, that is perhaps the hardest one, because you actually have to understand what happens in the quadratic situation, right? But we know, so that's just a usual circle. But the other two are easier. And in fact, maybe the infinity one is the easiest. Just think about what happens.
It makes us.
So I'm taking distance from the origin. So that just means the length of the vector itself should be less than or equal to, let us say, r, right? So what is the length of the vector? There are two coordinates. The infinity norm says that just take the larger of the two. So that means that the larger of the, so let's say what's not in there. The larger of those two things cannot be distance. So you cannot go in the x direction. You cannot go more than r, nor can you go more than r, the distance r in the y direction. So what is left?
A square.
I mean, it's just a square.
It's just a square box, right? Okay. So can I be adventurous and let's do the following. Maybe we'll color code these things. So so let's have that to be, so let's have that to be 1 red. Okay, but I actually talked about the infinity one first, right? So let's do that. So this is what happens. Is this okay? And this distance is just r. Okay, then let's do the.
Excuse me, sir.
Yes.
Can you please explain once more this norm?
Okay. So this is the set of all points. So let's look at the definition of the open ball. What am I saying? The ball is all those points that are distance at most r from x, but here the center is the origin. So I'm simply taking the set of all vectors whose length is less than or equal to r. But what is the length? The length is defined to be the maximum of the coordinates. That means the larger of the coordinates has to be less than or equal to r. So what this means is that your x coordinate also has to be less than or equal less than r, and the y coordinate also has to be less than r. Because if either one of them is r or more, then the condition is not met. No.
Yes, I get it now. Okay, sir.
So, and also it's important to say that what I have is the inside of what I have written. So the green thing itself is not in the open ball. However, if I take the closed ball, then it will be the green thing along with whatever is inside. Okay, so then this is the, okay, so now this is going to be terrible, but especially drawing on this iPad, but hopefully my circle is not going to be too bad. Oops, terrible. Okay, I hope it's acceptable. Okay, and let's now do the first one. So what is this saying? So let's just draw this here. So this is the set of all x comma y using the such that what happens? The norm of this point, the norm of this vector is less than 1. But what is the norm? It's the sum of absolute values. So we are saying absolute value of x plus absolute value of y is strictly less than r. So what is that? Let's look quadrant wise, right? So then it will be easier. So if I'm in the first quadrant, then absolute values of x and y are just x and y themselves. So what we are saying is that the sum of x and y is less than r. What is that? What is the boundary? That
A
is
line passing through r comma 0 and 0 comma r.
right, exactly. So it is really just this. And when you say less than, what you're going to get is that the part that is to the left and below of this line. Correct. And so then you just do the same thing in other things. And what you see is that it is going to be. So these are, let's just say that these are parts inside. So this is R minus R minus R, R. Parts of the plane inside respective regions. Okay, so all right, so this is all okay, all fun and games. The point is the following. So you see the distances are different. However, if I, in some sense, so the question that was asked earlier, that does the notion of convergence depend on which norm I take? And the amazing answer is that it does not. If a sequence, let's go back to the definition of convergence. So this definition of convergence depended on, see these red vertical double lines, that could be any norm, and I can make the same definition of convergence with respect to that norm. So it might seem that if I take different norms, then I will get different notions of convergence, but that is not true. The notions of convergence are going to be absolutely the same. And we can see this in examples by looking at the following. You see, just look at this interval. What are we saying? We are saying that for S to be the limit, what has to happen? No matter how small a region I take around my claimed limit, eventually the entire sequence has to fall in that region. Yes? Okay. The only thing that is different is what does it mean to be small? Okay. So now let's go and look at what happens if I use these different notions of distance. So let us suppose
for P in the range 1, 2, they will like the circle. It won't be a circle, but the line would pass between the red and the blue, right?
Correct, exactly. So now you see,
for P less than 1, it will be inside the square. And from here, can we like get some intuition about the complexity and proving that whole time?
Absolutely. So let me just rephrase that. What he is saying is that the red to blue to green, if you see the numbers are increasing, the value of P is 1 to 2 to infinity. And somehow what seems to be happening is that these boundaries, they're bending outwards. Correct? So this is what is going to happen. And you can maybe, take some, just plot it somewhere online or whatever, and then see what these balls are for various values of P. And then you will see that this is exactly what is happening. The boundaries are going to get bent outwards, but it is going to be some kind of oval shape. Okay. This also tells you what is happening as, so somehow that limit as P goes to infinity seems to make sense now visually. So this is one point. So first see this visually and then try to prove it. Second thing is that he also said that so going with the trend in the other direction, if P is less than 1, then that straight line maybe will start getting bent inwards. And you will have this shape where the corners will still stay. Okay. And maybe that has something to do with, somebody said convexity. And so maybe that will tell you why triangle inequality is problematic in that situation. Okay, so good. Carry out all of these experiments. Okay, but let's come back to this what we were saying. So suppose there is some sequence that converges to 0. Right? Visualize it with respect to usual distance. What does that mean? It means that if I draw an ordinary circle around the origin, then no matter how small I draw the circle, because remember, that's what it means, right? The norm being small, that just means you're in a small circle. No matter how small a circle I draw, the points of my sequence are eventually going to land inside that circle, right? That's what the sequence converging to 0 means. So picture some sequence in the plane, right? Something that is falling into 0. Okay. So, but just think about this. So no matter how small circle I take, eventually this sequence falls in the circle. If instead of that circle, if I start taking those red diamonds, will the same thing be true or not? Okay, let's see. So I'm just going to do this elsewhere. I don't want to spoil this nice picture, but let us say I have a, let's suppose I'm given a challenge circle and eventually all points fall inside this, right? Okay, good. But, and this is going to happen for all circles. But now let us suppose I'm given a challenge diamond and let's say this is the diamond, right? With the same
So
radius.
you can just take a circle that's smaller than the diamond.
Exactly. So you see, the point is for the same radius, for the same challenge, maybe this diamond will not work from that point onwards. But the point is I can just take a circle inside. And then a diamond inside that. You see, so that is the idea. That any circle can be sandwiched between two diamonds. And any diamond can be sandwiched inside two circles. And if you write this down, what this means in precise terms, then this is exactly going to give the answer to his question, that convergence with respect to the norm 1 and convergence with respect to the infinity norm, they're both going to give the same results for convergence. And for 1 and 2. And the same thing is going to be true for infinity, because boxes are the same. I can make the boxes also keep getting smaller and smaller to fit boxes inside circles and circles inside boxes. Okay. So this is one nice thing, but it gets better than that. So this just says, assuming our pictures, that for the family of norms that I did define here, namely these subscript p norms, where p is any real number from 1 to infinity, including infinity, the notion of convergence is the same. It gets better than that. It actually doesn't matter. It's for a finite dimensional vector space. Any norm that you define will give you the same notion of convergence. So, fact. To be proved later. Norm linear space is independent of the norm chosen. That sentence didn't come out very well, but you see what I'm saying. That if there are multiple norms on the same space, then whatever is convergent with respect to one stays convergent with respect to the other, and vice versa, right? I mean, and not only that, the limit also stays the same. So this is something that we will see. Okay, so okay, sorry, I'm almost out of time. Okay, actually out of time. Maybe just give me a couple of minutes. So many fantastic things, but life is even more fantastic. So far, the norms that we defined, so they were all on finite dimensional vector spaces, right? By the way, if I take a complex vector space, the same formula will work. Just interpret the absolute value to be absolute value of complex numbers. But, and this is one great thing, there is no reason why I cannot consider the notion of norm on an infinite dimensional vector space. Okay. Now you can wonder, how can I define a norm? So will this work? I take an infinite dimensional vector space. Will those p norms work?
Sir, it depends
we
on the
add
vector
those?
space, right? Oh, sorry.
Oh, sorry.
No, sorry. The definition as it is made here. Let us suppose I just take R infinite sequences of real numbers.
It
Will this
doesn't
definitely
quite work.
It should work, sir. Yeah.
So it shouldn't.
Okay, so you see both answers are right in a way. It will work, but it will give norms only of some vectors, you see.
Yeah, and the
but
equivalence
sequence will
won't
converge.
really hold true, right? When it's for infinite dimensional vector spaces.
Okay, but one thing at a time. I mean, for equivalence, I first have to have the norm. I just cannot add infinitely many things.
Sir, we
Yeah, so-
integrate instead of adding.
So I cannot do this with P, a real number P. Maybe it will depend. Perhaps I can define norms only of some sequences, where that infinite sum converges.
Right, sir. Yeah, sorry. I mean, I guess that's
Right.
what I meant. It's not for like any vector in. I don't even know how you define R infinity.
Okay.
But like,
Now R infinity is okay. That is not a difficult thing. In fact, you have defined R infinity. It is the space of all sequences.
oh, right, sir. Yeah.
Right. You can add component wise. You can scale component wise. Okay. All right. So we should sort of draw this discussion to a close, to sort of close the class formally, and then we will have we'll continue. But what I continue for this discussion. But what I wanted to say is that it is possible to define norms on infinite dimensional vector spaces. For example, I just said no. So okay. So here's the thing. How about this definition of infinity? Okay, so that's also not going to work. But if you have bounded sequences, right, then I can define that norm. So okay, so there are is the set of all bounded infinite sequences a finite? Is it a vector space?
Yes, vector space.
Yeah, because you see, so what does bounded mean? It means that every slot is less than some number, let's say 1,000,000, right? Absolute value. If I add two such things, such a thing will also be bounded. Just add the bounds. If I scale the bound, okay? And now this infinity norm, it's going to work on that, right? I can take soup, okay? So nice, but it gets even better than that. So you should try to think of the following example. Suppose I take all bounded functions on, suppose I take all, sorry, I just gave the game away. Suppose I take all continuous real valued functions on a closed interval 0, 1. Such a function is bounded, right? It's a continuous function defined on a closed interval. So you should just see that this is also a vector space, and I can define this infinity norm even for that. Don't take supremum of all the list because there is no list here, but still such a function will attain its, is bounded and will attain its maximum value, right? So just take the maximum value. It's an extremely infinite dimensional space here, but we do want to do analysis on such things too. So perhaps this is the most persuasive example as to why having this normed linear spaces is an interesting thing, because we can start doing estimation, convergence, distances, convergence in many more spaces than what one would think. You can even talk about functions converge, a sequence of functions converging to other functions. You can think of now a ball of functions. You take a function and what are all the functions that are within a certain radius of that function. All those notions make sense and we can do analysis with this. Okay, so with that, let's stop for today.